Humanity has been fascinated, and let's be honest, pretty intimidated by fire since the literal dawn of time. We usually think of it as this wild, unpredictable force of nature, right? Well, in today's explainer, we're not looking at it as some mysterious elemental magic. Actually, scratch that, we're doing the exact opposite. We're breaking down the exact observable mechanics of fire using some really solid foundational data from OSHA, MarineSite, and Explore Labs. Our goal today is to give you a crystal clear, structured understanding of exactly how combustion works. Because as you'll see, once you understand the strict biology of a threat, you are completely empowered to control it. Okay, let's dive into this directly with our core thesis, pulled straight from our source material. OSHA guidelines anchor all fire safety in one absolutely foundational concept, the fire triangle. This concept says that fire requires three things: heat, fuel, and oxygen to sustain combustion. This single sentence is literally the bedrock of all fire extinction theory. It tells us that fire isn't just this random event that happens to us, it's a highly specific chemical recipe. Think of it like baking a cake. If you leave out the flour, well, you don't get a cake. Fire works the exact same way. If you don't have all the specific ingredients present at the exact same time and in the exact right proportions, the whole thing just fails. The fire cannot exist. So, what does fire actually need to survive? Notice I deliberately used the word survive there. I want us to start framing fire almost like a living, breathing thing. Just like any living organism, it requires specific food and environmental conditions to thrive. It has a literal anatomy. When we stop looking at a burning room as a chaotic disaster and start looking at it as a hungry organism consuming a very specific diet, our entire approach to fighting it flips from panic to pure logic. All right, let's kick things off with Section 1, the anatomy of fire. To really wrap our heads around this anatomy, we need to anchor ourselves in the exact scientific terminology used in the Explore Labs resource. We're talking about combustion. So combustion is the chemical process of fire. When you see a flickering flame, you aren't just seeing glowing air. You're actually witnessing combustion happening in real time. It's a rapid chemical reaction where a substance combines with oxygen, and that releases energy in the highly visible forms of light and heat. And just like all chemical reactions, it follows strict, unbending scientific rules. It simply cannot cheat its own chemistry. Let's move to Section 2 and see how this builds into our three famous pillars: heat, fuel, and oxygen. First up is heat. Heat is the absolutely critical ingredient required to kickstart and then sustain combustion. But where does this heat actually come from in the real world? Well, according to the OSHA and MarineSite data, it's not always an obvious open flame. No way. It can be a tiny, almost invisible electrical spark from a frayed wire. It can be intense electrical friction. It can even be a hot mechanical surface in a ship's engine room. Heat provides that initial energy spike that raises a material to its ignition temperature. Without that initial burst of thermal energy, the chemical reaction just stays dormant. The fire simply can't begin. Next, we pivot to fuel. If heat is the spark, fuel is the food. This is the combustible material itself, the physical matter that's actually burning. Now, what's really interesting here is that fuel isn't just, a generic pile of wood. OSHA guidelines categorize fuels into highly specific classes, and these dictate exactly how dangerous the fire is going to be. So you have Class A fires, which are your ordinary combustibles like wood, paper, and cloth. Then you have Class B, involving flammable liquids like gasoline or oil. Class C fires involve energized electrical equipment. There are even Class D fires for combustible metals and Class K for cooking oils and greases in commercial kitchens. The exact nature of that fuel fundamentally changes the behavior of the entire fire. And finally, we have the third element, oxygen. Fire literally breathes. The oxygen present in the air around us reacts with the heated fuel to release more heat, and that creates a self-sustaining loop. But check out this fascinating data point from our safety sources. The air we breathe normally contains about 21% oxygen, right? Well, most fires only require about 16% oxygen to actively burn and sustain themselves. To put that into perspective, a fire can completely thrive in environments where a human would quickly suffocate. So these three specific components, heat, fuel, and oxygen, must combine in the exact right way to bring the fire to life. All right, this brings us to Section 3, where we get a bit of a plot twist: the fire tetrahedron. Now, what's really interesting about this slide is the evolution of the science itself. For decades, that traditional three-sided fire triangle was the absolute standard in safety education. But modern fire science introduces a more advanced model, the fire tetrahedron. So a tetrahedron is a four-sided pyramid. It takes our three base ingredients, heat, fuel, and oxygen, and adds a fourth crucial dimension to the whole shebang, the uninhibited chemical chain reaction. Why did science add this? Well, because as a fire burns, the fuel breaks down into gases and free radicals. These radicals react with oxygen, releasing more heat, which breaks down more fuel, in this continuous, massive feedback loop. Fire isn't just about ingredients sitting passively in a room. It's about this continuous, uninterrupted molecular interaction between them.
Okay, let's pivot in section 4, defeating the triangle. And this brilliantly illustrates the entire logic of fire extinction. If fire requires those structural pillars to exist, defeating it is elegantly simple in theory. You just break a pillar. But how does this translate to the real-world tools mentioned in our marine site and OSHA sources? Well, you extinguish a fire by removing the heat, which is exactly what spraying copious amounts of water does. It absorbs the thermal energy. You remove the fuel by physically separating the combustible material from the flame, like, say, shutting off a gas valve. You remove the oxygen by smothering the area, which is how a CO2 extinguisher or a heavy layer of fire-retardant foam works. And for that tricky fourth pillar, the chemical chain reaction, modern firefighters use specialized clean agents and dry chemicals that interrupt the fire at a literal molecular level. Breaking any single one of these pillars logically and immediately halts the entire combustion process. So the crucial point is that knowing this anatomy transforms a terrifying force of nature into a highly manageable structural equation. Fire requires heat to spark. It requires a specific class of fuel to consume. And it requires at least 16% oxygen to breathe. Together, these elements sustain the rapid chemical process of combustion and keep that chain reaction alive. Extinguishment is simply the deliberate, calculated act of breaking that cycle. Understanding these core takeaways isn't just academic chemistry, guys. It is the fundamental, actionable key to practical safety and survival in literally any environment. I want to leave you with a final thought to test your situational awareness based on the structural breakdown we just explored together. If a fire sparked right where you are sitting, right this very second, which part of the triangle could you realistically break? And what exact tool around you would you use to do it? Keep that question in the back of your mind as you go about your day. Thanks so much for joining me on this explainer, and keep observing the hidden structures of the world around you.